So introduction part. So I want to discuss something related to the time delay systems. Uh, the robust control of time delay systems has been a very active field for the past 20 years. It has owned many branches. For example, stability analysis, stabilization, design, H infinity control, passivity and dissipative control, and reliable control, guaranteed cost control, H infinity filtering, Kalman filtering, and stochastic control. So, in many physical and biological phenomena, the rate of variation in the system states depends on the past states. So, the characteristic is called the delay or a time delay. And a system with a time delay is called time delay systems. So, regardless of the branch in mathematics, stability is the foundation for the time delay systems. So, the important developments in the field of time delay systems that explore new directions have generally been launched from a consideration of stability as a starting point. So research on stability of time delay systems began in 1950s, first using the frequency methods and later also using time domain methods. So the frequency domain method have the limited applications. So whereas that in terms of time domain approach, we have so many applications, and we have to given an application in terms of physics as well as biology. So frequency domain methods determine the stability of the system with from the distribution of the roots of the characteristic equation or from the solution of a complex Lyapunov matrix equation. So they are suitable only for the systems with constant delays. Main time domain methods are Lyapunov-Krasovskii method functional as well as the Lyapunov-Razumikhin methods. So they are the most common approaches to the stability analysis of time delay systems. Since it was very difficult to construct a Lyapunov-Krasovskii functional and Lyapunov functions until 1990s, then the stability criteria obtained were generally in the form of existence conditions, and it was impossible to derive general solutions. After that, the Rakkiyappan equations and linear matrix inequalities with MATLAB toolboxes came into use, and the solutions they provided were used to construct Lyapunov-Krasovskii functionals and Lyapunov functions. So these time domain methods are very important in the stability analysis of linear systems as well as the non-linear systems. So stability analysis for the time delay system. Here we consider a linear system with the time delay x dot of t equal to a into x of t and ad into x of t minus h, where x of t is the state vector and h positive is that delay of the state of the system. That is, this is denoted as a discrete delay. So phi of t is the initial condition, and A and AD are the n by n matrices with real entries and are the system matrices. So the future evolution of the system depends not only its present state, but also its history. So the main methods examining its stability can be classified into frequency and time domain. So the frequency methods are I told that. So it depends only on the characteristic, the solution of the roots of the characteristic equations. So here the necessary and sufficient condition for the stability of the system is the eigenvalue of A plus AD, the matrix A plus AD. So we have to find an eigenvalue of the combined matrix. So which is negative. So the eigenvalues are negative, or the eigenvalues are having negative real part, then we can say that the system is stable. When H positive, the frequency domain method yields that the result of the system 1 is stable if and only if of all the roots of the characteristic function, the determinant of lambda minus a minus ad into e power minus h lambda should be equal to positive or negative real parts. So, however, this equation is transcendental, which makes difficult to solve. So whereas in time domain methods, there are two methods are very popular, are very famous in the field of stability analysis. So the one is
seminar tыңдап отырмыз да.
No, continue. Okay. So there are two methods. One is the Lyapunov-Razumikhin and then the Lyapunov-Krasovskii stability theorems. So they were established in 1950s by the Russian mathematicians Krasovskii and Razumikhin respectively. The main idea is to obtain a sufficient condition for the stability of system, one by constructing an appropriate Lyapunov-Krasovskii functional or an appropriate Lyapunov function. MATLAB toolboxes appeared or made it is easy to construct Lyapunov-Krasovskii functionals and Lyapunov functions, thus greatly promoting the developments and applications of these methods. So among them, two classes of sufficient conditions have received a great deal of attention. So one is the delay independent stability and another one is the delay dependent stability. So the delay independent one is nothing but the independent of the length of the delay. Whereas the delay dependent is it depends on the delay. So these delay terms, delay values are appear in the matrix inequalities. So the Lyapunov-Krasovskii functional candidate can be generally chosen to be like this in equation 3. So it is a quadratic term, so which was used by the great mathematician Lyapunov, and then we can add another one more integral quadratic terms. So this is nothing but integral t minus h to t, so x transpose of s q into x of s ds, where p and q are the Lyapunov matrices, and those two are the positive definite matrices. And xt denotes the translation operator acting on the trajectory xt of theta equal to x of t plus theta, where theta belongs to minus h comma 0. Okay, so calculating the derivative of v1 of xt, so along the solution of the system and restricting to less than 0 yield the delay independent stability condition of the given system. So this is the delay independent condition. So here there is no delay. So there is no h value appearing in this matrix inequality. So this means that a matrix is less than 0 is nothing but this would be a negative definite matrix. Or in other words, we can say that we have to find the eigenvalues of this matrix. So all the eigenvalues having negative real part. So since then we can say that the given system is stable. So since this inequality is linear with respect to the matrix variables p and q, it is called an LMI, linear matrix inequality. If the LMI toolbox of MATLAB yields solutions to LMI 4 for these variables, so then according to the Lyapunov-Krasovskii stability theorem, the system 1 is asymptotically stable for all h greater than or equal to 0. So the hot topic in control theory are delay dependent problems in stability analysis, robust control, H infinity control, reliable control, guaranteed cost control, saturation input control, and chaotic system control. Since 1990s, the main approach to the stability of delay dependent stability has involved the addition of Lyapunov quadratic double integral terms to the Lyapunov-Krasovskii functional 3. So this is the double integral term. So this is the double integral term, quadratic integral term. So we have to use this term so for getting the delay independent stability of the given system. So we have to take the derivative of v2. So we can we can use the Newton-Leibniz formula. So we can separate. Using the Newton-Leibniz formula, we achieve the equation 6. So after that, for this term, we have to apply some more interesting inequalities which are available in the literature. So the first basic inequality is the for all AB belongs to R, and R is a positive definite matrix. So then this inequality always holds. So and then we have another one more interesting inequality which was introduced in 2002 by June Moon Park. He is a Korean mathematician. He has introduced one inequality which is nothing but the Park's inequality. And also in 2003 itself, another one more inequality was introduced by Moon et al. So this inequality is called Moon inequality. With this, we have 4 kinds of model transformations. So this is the first kind of the model transformation. The given system 1 can be written as like this. So x dot of t equal to a plus ad into x of t minus ad into integral t minus h to t. So a into x of s plus ad into x of s minus h into ds. Just we can substitute this integral in the equation 1. So we can get the equation number 10. So the following Lyapunov-Krasovskii functional could be constructed for deriving the delay dependent stability. So the 11 is the equation 11 is the Lyapunov inequality with v3 of t equal to the double integral quadratic integral term. So we are taking the derivative of this Lyapunov function. We arrive the equation 12. So, and then we can use the basic inequality which was defined in equation 7. So then we can get the integral inequalities eta 1 and eta 2. So applying these inequalities in equation 12, in terms of these places, so we can have a linear matrix inequality. So with this linear matrix inequality, so we have to find the stability of the system equation 10. So these are the main observations I have noted when we are using the model transformation 1. So the purpose of a model transformation is to bring the integral terms into the system equation so as to produce both cross terms and quadratic integral terms in the derivative of the Lyapunov-Krasovskii functional along the solution of the system. So the bounding of the cross terms eta 1 and eta 2 eliminates the quadratic integral terms in the derivative of the Lyapunov-Krasovskii functional, so thereby yielding a delay dependent condition. So this is the main advantage of while using the model transformation number 1. So the next one is the model transformation number 2 is nothing but the equation of the form in which is given in equation number 13. So Professor Gu wrote an interesting book for stability analysis of time delay system. He has pointed out since the model transformations 1 and 2 introduce the additional dynamics into the transformed system, the transformed system is not equal to the original one. So yeah, here you have to take is not equivalent to the original one. So now we have to define the new model transformation number 3, which is of the form in equation is given in the equation 14. So the Lyapunov-Krasovskii functional for this equation can be constructed as in equation 15 with the term v4 of xt equal to the double integral term having the derivative. So x dot of transpose of s z into x dot of s ds d theta. So while using this term, we have some trouble while eliminating this integral. So then we can use some interesting inequalities as defined before. So using those inequalities, we have to derive. So we can achieve this term, and then we can use for eliminating this term. Then we can use the different inequalities like basic inequality, Park inequality, or Moon inequality. So we could achieve some results based on while using the different inequalities. So the bounding of the cross term. So this is a cross term. So we have x transpose of t as well as x dot of s. So we have the cross term. So eta 3 eliminates the quadratic integral term in the derivative of the Lyapunov-Krasovskii functional, thereby producing a delay dependent condition. So after the model transformation 3, the transformed system is equivalent to the original one. So in addition, after the transformation of system 1 into 14, so when dealing with the term h into, so here you can see this term, the last term of the function 5. The h into x transpose x dot transpose of t r into x dot of t in the derivative of v of xt, system 1 is used as a substitute for the system 14. So that is to obtain the 14, the state delay term x of t minus h in system 1 is replaced by the Newton's Leibniz formula, but x of t minus h is not replaced by the in the derivative of v of xt. So this consistency in the elimination of the integral terms leads to the conservativeness. So this is the final one, the model transformation 4. Just we can substitute the right hand side should be y of t. So then y of t can be expressed as like this. So then Friedman was employed the following generalized Lyapunov-Krasovskii functional, where we can get an augmented system, and then we are using these vectors with the derivative of v of xt along the solution of the given system 17 can be expressed as this sigma plus eta 4 minus this integral term. So then where the remaining functions are defined here. So here also we can have a bounding cross terms. So eta 4. So we have to eliminate this term the quadratic integral term in the derivative of the Lyapunov-Krasovskii functional 19, thereby producing a delay dependent condition. While we eliminating this term, then we can get the delays can be appeared in the linear matrix inequalities. So these are the observations. So when double integral terms are introduced into the Lyapunov-Krasovskii functional to produce the delay dependent conditions, delay dependent stability conditions, it results in quadratic integral terms appearing in the derivative of that functional. So model transformation emerged as a way of dealing with those quadratic integral terms. So more specifically, the purpose of model transformation is to bring the integral terms into the system equation so as to produce cross terms and quadratic integral terms in the derivative of the Lyapunov-Krasovskii functional. So then bounding of the cross terms eliminates the quadratic integral terms. So the basic feature of all model transformation is that they produce cross terms in the derivative of the Lyapunov-Krasovskii functional. However, since no suitable bounding methods have yet been discovered, the bounding of cross terms results in conservativeness, and attempts to reduce the conservativeness have naturally focused on this point. So now we have an interesting formula which is known as a free weighting matrix. So from the Newton-Leibniz formula, the following equation is true for any matrices n1 and n2 with appropriate dimension. So we have to write this is our original system, and then just we can use the Newton-Leibniz formula. This integral t minus h to t x dot of s ds can be expressed as which is equal to x of t minus x of t minus s. Then then we can get a 0. So then you can multiply any terms like this. Multiply any terms like this. So therefore, we have you have to multiply by any terms with 0. You can get the 0 term. So we adding this term in the right hand side of the derivative of the Lyapunov functional. So we adjusting the cross terms as well as the main diagonal terms. So we could achieve the stability or delay dependent stability in a great manner. So now we add the left side of this equation to the derivative of the Lyapunov-Krasovskii function. The fact that the n1 and n2 are free and that their optimal values can be obtained by solving LMIs overcomes the conservativeness arising from the use of the fixed weighting matrices. So since the two sides of the system equations are equal, the free weighting matrices thus express the relationship among the terms of that equation. So that is from system equation 1, the following equations are true for any matrices T1 and T2 with appropriate dimensions. So we can use the free weighting matrices in another form. So just we can take the terms from the given equation 1 to the left hand side. So you can get a 0 matrix here. So then 0 vector here. So you can use just simply the 0 value with this term multiplying by any times like this. So and from the Newton-Leibniz formula, the following equation is also true for any matrices n1, n2, and n3 with this 0 vector, multiplying with this 0 vector. So you can get a zero real number. So you can add that real number to the derivative of the Lyapunov-Krasovskii function. We could achieve the stability results with less conservative. So this is for these things for applied in linear systems, whereas the theory of Lyapunov-Krasovskii as well as the Lyapunov-Razumikhin conditions for is applicable for continuous time non-linear systems also. So consider the continuous time system x dot of t equal to f of t comma xt with the initial condition x of t naught equal to x naught. So where x of t is the state vector, f is a non-linear function. So if the solution exists, then the f should be continuous, and we need the uniqueness for this system. Then this f should be Lipschitz continuous. So the point xe in Rn is called an equilibrium point of the system that should satisfy the function f of t comma xe should be equal to 0 for all t greater than or equal to t naught. So we have the famous definition in the sense of Lyapunov for the stability analysis. So there exists a delta 1. If given any epsilon positive, there is a delta 1 such that norm x of t naught is less than delta, which implies that norm x of t is less than epsilon for all t greater than or equal to t naught. Then we can say that the system is stable in the sense of Lyapunov with respect to the equilibrium point x equal to 0. If the system is stable and if there exists a delta 2, so delta 2 is nothing but it depends only on the initial time t naught. So such that the norm x of t naught is less than delta 2, which implies the limit t tending to infinity x of t equal to 0, then we can say that the system is asymptotically stable at the equilibrium point x equal to 0. So we have the third definition, which is nothing but the system is exponentially stable. So this is the exponentially decay term, and then this alpha is called the exponentially decay rate. So then we can accordingly we can define uniformly stable, uniformly asymptotically stable, uniformly globally exponential stable in a great manner with respect to the condition that the delta which depends only on the points of time. So not on delta depends only on time. So then we can define the uniform stable, uniformly asymptotically stable, as well as the uniformly exponentially stable. So these are the figure illustration for the stability in the sense of Lyapunov. This is a notion for asymptotic stability, and this is the same thing has applicable for continuous time discrete systems. Continuous time discrete systems. So the continuous time discrete system is described in equation 27 with respect to the initial condition x of k naught equal to x naught, where the solution exists when f is continuous, and the solution of this system is unique when f is Lipschitz continuous. So these are the another definition for the system 27. And this is a figure representation for the stability of the discrete time system in the three-dimensional space. So the first one is in the space plane, and then the second one is the three-dimensional system, and then this is for the asymptotic stability. Yeah. So now, so coming to the Lyapunov stability. So the Lyapunov constructed an energy function. So that is the expressed in terms of the state energy. V of x of t, which should be positive, and maybe it should be equal to 0. So if x not equal to 0, then it should be positive. If x is equal to 0, then it should be equal to 0. So now we have to find the derivative of this Lyapunov function is less than or equal to 0. Then the system at the equilibrium, then the stability at the equilibrium point can be proven without using the information on the solutions of the motion of the equation of the system. So this is the key point. So without knowing the solutions, the solution behavior or solution dynamics, the dynamic solution, the dynamics of the solutions, so we can achieve the stability results in terms of Lyapunov theory. So there are two methods. So one is the Lyapunov indirect method and Lyapunov direct method. The Lyapunov indirect method says that if you have a nonlinear system, first of all, we have to linearize the given system. After that, we can apply the Lyapunov theory. So that method is called Lyapunov indirect method. Whereas the Lyapunov direct method, you have a nonlinear system. So the if you have to take the same nonlinear system, and we have to apply the Lyapunov theory for the given nonlinear system. So that method is called that approach is called the Lyapunov direct method. So here consider the this theorem. So consider the system 23. So with the condition f of t comma 0 equal to 0 for all t, which means that the equilibrium point of the system xc equal to 0 if there exists a positive definite function v of t comma xt, and the derivative of the positive definite function, which is nothing but d by dt of v of t comma xt is negative semi-definite, then the system is stable at the equilibrium point x equal to 0. Then if it is asymptotically stable, so then the derivative of the Lyapunov functional is negative definite. So it should be less than 0. So then the system is asymptotically stable at the equilibrium point x equal to 0. So the system is asymptotically stable at x equal to 0, and v of t comma x of t tending to infinity as norm x tending to infinity. The system is globally asymptotically stable at the equilibrium point x equal to 0. So we have another one more theorem for discrete time system. So the same thing has been applied for the same notion has been applied for the discrete time systems. So here now we have to consider the retarded functional differential equation. So we have to apply the Lyapunov theory, the Lyapunov-Razumikhin method as well as the Lyapunov-Krasovskii method for the retarded functional differential equations of the type which is given in equation 32 x dot of t equal to f of t comma xt, where x of t is the state vector and f is the map is from r cross c to rn. So the equation indicates that the derivative of the state variable x at time t depends on t. Then x of psi lies between x of psi for psi lies between t minus h to t. So we have the unique, we want to derive the uniqueness of the given functional differential equation. So this is nothing but the definition of Lipschitz condition. Then the concept of stability is defined in definition 3. And this is the Lyapunov-Krasovskii stability theorem. So for a time delay system, the Lyapunov functional is a functional v of t comma xt that depends on xt and indicates how much xt deviates from the trivial solution. Then this type of functional is called Lyapunov-Krasovskii functional. So more specifically, we have to take let v of t comma phi is a map from r cross t to c to r be differentiable, and let xt of tau comma phi be the solution of the retarded functional differential equation 32 at t at time t for the initial condition x tau is equal to phi. So calculating the time derivative, so the time derivative can be calculated as like this, and the derivative of this functional is non-positive, then xt does not grow with t, which means that the system under consideration is stable in the sense of definition 3. So this is the famous theorem for Lyapunov-Krasovskii stability. Here consider, suppose that the function f functions where u of tau and v of tau are positive for tau positive and u of 0 v of 0 equal to 0. If there exists a continuous differentiable function v from r cross t so r such that u of norm phi of 0 is less than or equal to v of t comma phi is less than or equal to v of norm phi, then the derivative of this functional is less than or equal to minus w of norm phi of 0. Then the trivial solution of 32 is uniformly stable. Similarly, we have to prove uniformly asymptotically stable with relaxing some condition. So, and also we have globally uniformly asymptotically stable with this condition. So the Razumikhin stability theorem, the Razumikhin theorem uses a function v of x to represent the size of x of t. V bar of xt equal to maximum of theta belongs to minus h comma 0 v of x of t plus theta. So this function indicates the size of xt. If v of x of t is less than v bar of xt, then v bar of xt does not grow when v dot of x of t greater than 0. In fact, v bar of xt not to grow, it is only necessary that v dot of xt not to be a positive whenever v of x of t equal to v bar of xt. So this is the Razumikhin theorem. And then we have to define a norm with respect to the definition of the norm. We have to define H infinity norm. This H infinity norm is applicable for the space of measurable functions f of s. We have to define norm f infinity equal to supremum of all s, the maximum eigenvalue of f of s such that the real part of s should be positive. So then the supremum should be is finite. So then this equation defines norm f infinity, the h infinity norm of the matrix function of f of s. This is the h infinity norm. The equation, the inequality 38 is the h infinity norm for the matrix functions. So we have to find the h infinity control for the following system: x dot of t equal to a into x of t plus bw of t, z of t equal to c into x of t plus d into w of t, where x of t is the state vector and w of t is a disturbance input vector and ABCD are the real matrices with appropriate dimension, and G of S is nothing but the transfer function matrix of the given system. So with this transfer function matrix, so we have to define the norm for this matrix. With this norm, we have to define a H infinity norm on G of S. So which is nothing but norm G infinity equal to supremum of all omega not equal to 0, norm Z of omega, the two norm of Z of omega divided by the two norm of the W of omega. So the H infinity norm reflects the maximum ratio of the output signal energy to the input signal energy, or in other words, the maximum energy amplification ratio of the given system. So this amplification ratio is called the disturbance attenuation level. So this can be defined here. So our estimation depends on H infinity control. So we have to establish the disturbance attenuation level gamma. So the LMI method, it is a powerful tool which is applied in the stability analysis of time delay systems as well as the control systems. So here the first Lyapunov linear matrix inequality is nothing but which was derived by the mathematician AAM Lyapunov in 1892 itself in the Russian literature. So this is nothing but the Lyapunov matrix inequality. So this is the first inequality, and then this inequality is called also called the linear matrix inequality. Here the matrix A is unknown and X and Q are the unknown matrices with appropriate dimensions. So here there are several kinds of LMI problems, linear matrix inequality problems. One is the LMI problem. The first one is the LMI problem, which is nothing but the feasibility of the problem. So mainly we are using this problem or this method for obtaining the stability analysis as well as the control analysis for the given systems. So the another two methods are, one is eigenvalue problem as well as another one is the generalized eigenvalue problem. So these are the another two different methods. Frequently this cannot be used in the literature. Mainly we are focusing on the first problem, LMI problem. So it is nothing but we have to establish the feasibility region for the given convex region for the given LMI problem. Yeah, so these are the famous lemmas. So the first one is this Kerr complement lemma. This is the most powerful tool in linear matrix inequality theory, and the lemma 2 is applicable for while we are doing the robust control for the given uncertain systems. So we want a system having the time dependent matrices. So we want to eliminate those time dependent matrices with this form. So then this can be removed from this F transpose of T. F of T is less than or equal to I. This condition has been imposing on this. Then we can get this kind of inequalities. So therefore, we can easily study the robust controllability for the given uncertain systems. So on lemma 3, it is also a powerful lemma which was used in the literature earlier. The lemma 4 is the S procedure, and the lemma 5 is the some basic inequalities. These inequalities always using while we are studying stability analysis of time delay systems as well as stability analysis of neural networks. Yeah, so we can have these are the simple. So this is a simple method for the time delay systems while using a Lyapunov-Razumikhin method. Just we constructing a Lyapunov. Here we have to take the system 62 is the given system, and then we construct the Lyapunov function, quadratic Lyapunov function. V of x is equal to x transpose of t p into x of t, and then we can achieve a linear matrix inequality of the form 65. So we are going to solve this linear matrix inequality using MATLAB LMI toolbox. Our aim is to find the unknown matrix P. So this is the procedure for deriving the theorem. And then according to this result equation inequality 70, the system is asymptotically stable. With respect to the derivative of the Lyapunov function should be less than 0. Okay, so this is another suppose if you are achieving this LMI, so then it can be while using a square complement lemma, then automatically we can achieve this inequality. So the square complement lemma can be applied for this inequality. We can achieve this inequality. So then it is very easy. So here in this case, the matrix inequality should be non-linear. Here you have P inverse as well as P. So there are two unknowns appearing on the same term. In the same term, you have two unknowns. So if you have two unknowns in the same term, it is not possible to solve those those terms. We cannot represent those terms in the LMI toolbox. So therefore, we want to replace this. This is a non-linear term. So therefore, we want to linearize this term. So if we are linearizing this term using square complement lemma, so then it could be very easily possible. So we can achieve this term. So then we can linearize this inequality. Then it is very easy to possible to write those things in terms of linear matrix inequalities, and then we can solve using LMI toolbox. So this is a method for generalized eigenvalue problem. So it is not necessary to can be used anywhere. So for a real life problem, having a control problem or the stability analysis of the given system. So this is a simple example. So here we have to take the system matrices like this, and then we can achieve the linear matrix inequality in proposition 4. So solving these inequalities, and then we can get the stability analysis of the given system. So similarly, we can have another one more model transform. Using model transformation, we can get the equation 76, and then we can solve. We can achieve the stability analysis of the given system. So similarly, we have different kinds of methods for a system having a time delays, single time delays. Yeah. Yeah, so these are the interesting books. So Heikin Gu and with Professor Vladimir Karitanov has written an interesting book which was published in Springer Birka user. So the stability analysis of time delay system. It is an interesting book. So one can easily to study and know about the stability theory in terms of linear matrix inequality. So this could be very useful for the introductory level. And also, this is also an interesting book which was written by Professor Emila Friedman. She is a Israeli mathematician. So she has done a lot of work in time delay systems. So currently, she is working something on observer-based control in parabolic partial differential equations. So, and then another one more thing is the robust control of time delay system. So it is also an interesting book. So it is also an introductory level of the time delay systems. Yeah, and then these are the some interesting articles. So always Professor Yang he has the father of introducing some integral inequalities in the linear matrix inequality theory. So he has done a lot of work in stability analysis of time delay systems. Yeah. So thank you. So thank you for your patient listening. So